Okay. So we just introduced the derivative. It is the answer to the rate problem, believe it or not, this innocent looking guy. Very important equation. It's called the limit definition of the derivative. It helps us to find the slope of the tangent line and by extension to find all of these things. I can also talk about some other applications. It turns out that the derivative is surprisingly useful. Sorry. We can talk about applications of the derivative. We'll see some of them in this class, or not. So physics is one. Physics engineering, of course. So things like motion. So for example, three very standard functions you will see in first semester physics within the first couple of weeks. You can talk about a function that measures the position of an object. Usually this is called S. It turns out if you take the derivative of S, S prime of t, you get a function that we call v of t, and that's actually the velocity. So this is just speed in a certain direction. And if you take the derivative of the velocity, you end up with a function that we call a of t, which is acceleration. So this is the position. This would be the rate of change of position. We call that velocity, or speed in a particular direction. And the rate of change of velocity is what we call acceleration. And so that's one common application of derivatives, is to talk about these three functions. So in your physics textbook, for those of you who might have to take physics, you talk about a lot of functions in the first chapter dealing with these guys, and all of those functions are derived using this guy, right? But you probably won't actually go over that in physics. They'll just say, here's the formula. And it's really a calculus. Calculus is how they figured out those formulas. We talk about economics, particularly marginal analysis. We'll actually be covering this in class. So the idea of a marginal function and what that can mean. So you'll see that here. You'll see it in population dynamics. Right, so you want to talk about how fast populations are growing and how this is affecting the environment or whatever. You can talk about certain behaviors of functions as well. And by extension, you can talk about the behaviors of the things that the functions are modeling. So you can talk about where a function might hit a maximum or a minimum, or talk about its concavity. We'll actually talk about a little bit about that as well. So I mentioned to you that the formula x equals minus b over 2a tells you about the vertex of a parabola, which ends up being the maximum or minimum point of the parabola, depending on if it's opening up or down. But there's no general formula like that for any other function. If we want to find the max or min of any other function, the derivative is basically how we're going to do it. By looking at the derivative and how it behaves, you can figure out a lot of other stuff. There are a lot of other things. Most of the applications we're not going to touch on. We'll touch on marginal analysis, we'll touch on this. We won't do much on populations. But there's a lot of benefit to figuring out rates of change, surprisingly. We have a lot of tangential benefits, pardon the pun. But right now, let's actually do some another application for you guys is related rates. We'll actually do that in class. So we'll be doing that. Another very important is optimization. That's a really big one, super important, but that's the next class. Class after this, we'll do that. We'll actually do related rates and margin analysis, some max and min stuff. But for now, I just want us to practice using the formula to find the derivative. This is something that's important that you're going to need to know, that's going to be on the test. Use the definition. So we're going to find the derivative of a bunch of functions. Let's talk about y equals 3. Y equals c, c a constant. Y equals x. Let's do y equals c. C is a constant. Let's just do those. These two are going to be annoying, so instead I'll ask you to use E. So we're going to use the definition of the derivative to find all of those. So for the most part, we are actually computing the limit of a difference quotient. So we're going to move relatively quickly because we've looked at difference quotients so often and we've been on limits for a while. So let's actually do that. First of all, for y equals 3, what do you think the answer will be? Just by your knowledge of what a derivative is. If I tell you the function is y equals 3 and I want you to find its derivative, what is the derivative of that function? What would you guess the derivative is? Yeah, based on the interpretations. I don't mean you should do the calculations. We're going to do the calculations. I mean, can you tell me what the answer would be before we do any calculations?
Is it 0?
Why would you say 0?
Because y equals 3 is a graph of a line and there's no slope.
Y equals 3 is just a horizontal line. Derivative is a synonym for slope. So me asking you to find the derivative of y equals 3 is exactly the same as me asking you to find the slope of y equals 3. A horizontal line has slope 0. Therefore, we expect the answer to be 0. but let's actually do it via the calculations. So we're going to do the limit of f of x plus h minus f of x over h, right? The limit part is important. So if this is our f of x, what is f of x plus h?
There's no h's there, because there's no other line, and that's what we're using, that h is supposed to be the distance between.
Yeah, well, what is f of x plus h? If 3 is f of x, what is f of x plus h?
Here, is the same line?
It's 3. What is f of x?
3.
That's 0. Right? You get 3 minus 3, which is expected. In fact, from B, if your f of x is a constant, any constant, pretty much your f prime is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. That's always going to be c minus c over h. You will always get 0. In fact, this is a rule that we can talk about now. I'll write it down. Usually I'll say the rules in Leibniz notation, probably the best way to memorize them, I think. The derivative with respect to x of a constant is 0. So I can express that as a rule. Let me just write down what this means. This says the derivative. It's going to show up. So basically this is saying the derivative with respect to x, right? We're always going to do single variable calculus, so it's always going to be with respect to one variable of c is 0. The derivative of any constant will be 0. Doesn't matter what the constant is. Could be 3, radical 2, 1.9, square root of 11. Any of these functions, if I find the derivative, the answer is going to be 0. So you can just know the derivative of any constant is going to be 0. Because a constant function is just a horizontal line, the slope of a horizontal line is 0. And derivative means slope, that's what it means. Okay. What about a constant times x? So let's say my function is a constant times x. What would you guess the derivative is? C, right? Because the function y equals cx is the equation of a line. We know the line equation is mx plus b, where m is the slope. M is the guy that's multiplying the x, so here you have c multiplying the x, so you'd expect the c to be the slope. But slope is another word for derivative, so let's actually see if that works out. F prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. That's the limit as h approaches 0. What is f of x plus h in this equation?
Of x plus h minus c times
No.
x.
What is f of x plus h?
C.
C.
There's no other line for h.
So let's go back. What does f of x plus h mean?
Plug in wherever there's an x,
Wherever there's an x,
plug in x plus h.
plug in x plus h. Do you see an x?
Yes.
Yeah, it's right
So
there.
it should
So what are we going to do?
f of x.
So f of x plus h means
C multiplied c times x plus h
there's an x right there, replace it with x plus h.
minus cx over h. So
Okay.
cx.
So what this gives us is what?
Cx plus ch minus cx over h.
This kills that.
And
You'll be able
ch.
to then cancel the h.
So
And so you just pretty much get the limit as h approaches 0 of c. Limit of a constant is the constant. Right? So no matter what the constant is, the derivative
it's going to
of
be
a constant times x is just the constant. In particular, the derivative of the function x is
C. Just X. Right.
8 times into the rule.
Um,
Derivative of a constant times x is just a constant.
so it's C.
So the derivative of x would be
It would be 1.
1, because there's a 1 in front
Yeah,
of
yeah,
it.
yeah.
Right? And again, if you look at y equals x, the slope is 1. Derivative just means slope. Right. So pretty much these, you should kind of know what the answer should be before you even do anything, because derivative just means slope. That's a horizontal line, slope is 0. That's a horizontal line, slope is 0. That's a line with slope c. So the derivative should be c. The derivative will give us the slope of the straight line in all these cases, right? X squared is not as obvious, right? What would the slope of that look like?
It would differ. It will be.
What we would do
The
is
derivative would be 2x.
we use the definition. So for d, if my f of x is x squared, and I want to use the definition of the derivative to find it, that means I'm going to use this guy. Limit as h approaches 0, f of x plus h minus f of x over h. This is the limit as h approaches 0. What is f of x plus h?
F of x plus h squared.
F of x plus h means I look at the formula, wherever I see an x, I replace with an x plus h.
So x
squared.
Yeah, x plus h squared.
You don't write the f again.
Okay.
Minus f of x is
X
that
squared over h.
h. How do I
X squared
simplify that?
plus
How do I take that?
2hx plus h squared.
X squared plus 2 is h squared minus x squared all over h.
And
Now
then
what?
you cancel x squared
Well, x squared minus x squared.
and cancel h.
Well, you can't cancel h, there's
Oh,
a
you
sum. You
factor.
can't cancel across the sum. So you factor out the h.
2x plus h over h.
Those cancel.
2x
What's
plus
the limit now?
2x plus h. And
Well,
then
we're
you
taking the
plug
limit
in
as x
0.
approaches 0. So we get
2x.
plus 2x. So the slope of x squared is 2x. And what does that mean? That is a formula for the slope of the tangent line. Meaning at any point along the curve x squared, if I want to know what is the slope of the tangent line at this point, that formula is going to tell me. So someone can ask the question, what is the slope of the tangent line to x squared when the x value is 3? It's 6, right? If I were to draw x squared, looking like that, and someone says, we care about x equals 3, and I care about the tangent line at x equals 3. What is the slope of that line? 6. I will just take 2 times whatever the x value is. This gives me the formula for the slope of the tangent line. We'll look at more of that in a bit. Right now we're just going through and doing some calculations. So to find the slope of x squared by the definition, first of all, notice that I keep writing this down over and over. It is something that you need to have memorized. Keep writing it down until you can recall it in your sleep. Okay, so you apply this and you get 2x, and that's the slope of x squared. And what that means is I can figure out what the slope of the tangent line is at any point at any x. What? We're taking the limit. What's happening with the limit? H is going to 0. Let's plug in 0. Now, I don't really like doing this one. Your book does a little proof, but it's, so here, suppose n is a positive integer. So there's something called binomial theorem, you don't need to know what it is. But it basically says something that looks like this, a plus b raised to the n. It expands into n plus 1 terms using the following formula. It will be n0 n0 plus n1 n minus 1 1 plus 2 n minus 2 2 plus dot 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 dot, and it will keep going until it gets up to n. So n minus 1 n minus 1 b to the 1 plus n to the n a to the 0 b to the n. These numbers here are the coefficients, and those are the terms. So for example, if you have a plus b all squared, this says this should be n choose 0, a squared, b to the 0, plus n choose 1, a to the 1, b to the 1, plus n choose 2, a to the 0, b to the 2. And in this case here, n is 2, so that's 2, that's 2, and that's 2. And it just so happens that this gives us the answer 1, that gives us the answer 2, this gives us the answer 1, and so we end up with a squared plus 2ab plus b squared. And that's, so they wanted to generalize that formula. So this kind of comes from, you can think of this as coming from something called Pascal's triangle. So there's a formula for this, but then I have to define something else for you to realize what that is. It's defined in terms of what we call a factorial. But another way you can actually construct the numbers is something called Pascal's triangle. Quickly telling you this because I don't know, might come in handy one day. So you start with a triangle of all ones, and then you can kind of build each new level in the following way. It starts with a 1, and for each new number, you add the 2 numbers on top of it, 2, and you end with a 1. So 1, add 1 and 2, you get 3, add 1 and 2, you get 3, and with a 1. 1. Add 1 and 3, you get 4, add 3 and 3, you get 6, add 3 and 1, you get 4, and with a 1. And you can continue this pattern. 1, 6, 15, 20, 15, 6, 1, etc. You can keep going and building up these triangles. And what you'll notice here, this actually tells you how to expand any binomial, right? So you can kind of think of this guy as going with a plus b all squared. The 1, 2, 1 are the coefficients, right? You can think of the third line, the line that starts with the 3 here, as telling you the coefficients of a plus b all cubed. So it turns out you would have, if someone asks you, expand a plus b all cubed, you know that there are going to be coefficients of 1, 3, 3, 1 in that expansion. And what you do is you start with one variable to the highest power and you count down. So you go a cubed, a squared, a, and a to the 0. Then you start with the other variable and start with the lowest power and count up. The lowest power being 0, so your b doesn't show up. B to the 0, b to the 1, b to the 2, and b cubed. And then you put a plus sign in between. That's how you expand these things. Right? So if someone were to ask you, what is a plus b raised to the 6th power? Now, you could multiply a plus b by itself 6 times and spend the rest of your night foiling, or you could realize that, oh, the coefficients are going to be 1, 6, 15, 20, 15, 6, and 1. And I will start with the a at the power 6, count it down, and then I start with the power of b and count up. and then just add all these. Right? So it gives a nice formula for expanding a binomial. So in other words, if I replace, for example, the A with X, and I replace the B with H, I can just go through and I can just replace all these guys here. So that's now X and H, and that's an X and an 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 H. Okay, so that is just to give you a quick overview of what I'm about to write down. Okay, so our goal is to now find the derivative of this, but I'm only going to show you what it breaks down to if n is a positive integer, and then I'll basically tell you this will work in general, because we don't actually know enough to prove the general case. But this is probably something you've seen in algebra at some point. I'm not sure what the algebra class is like, but the binomial theorem it's a very common thing to teach in an algebra class. Now if you look at E, f of x equals x to the n. So we want to find this derivative. This is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the limit as h approaches 0 of x plus h to the nth power minus x to the nth power all over h. And now I'm going to apply that rule. So this kind of thing I can expand using the binomial formula. This is going to be n0 x to the n plus n1 x to the 1 h x to the n minus 1 x to the n minus 1 times h to the 1 plus n2 x to the n minus 2 h to the 2 plus dot dot dot. It'll go all the way until it ends up with n h to the n. So now you'd realize is that this will look like Pascal's triangle, right? That these are the numbers. It always starts with a 1, right? Then the n, then and it always ends with a 1. So those are the important numbers that you need to care about. So basically what you have here is 1x to the n minus x to the n. So this is going to cancel with that. You will also notice that every other term is going to have an h in it. So now this becomes, I can factor out that common h, and I'd be left with nx to the n minus 1 plus n choose 2 x n minus 2 h to the 1 plus dot 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 1 h to the n minus 1. This would cancel. And now you'd actually plug in h equals 0. Now if I go here and I plug in h equals 0, what do I have left over? Right, nx to the n minus 1. So this implies the following rule. And I'll just say this works in general. Even if n is not a positive integer. Unfortunately, we don't know enough for me to actually prove that to you. You'll need to know about exponential functions and log functions and some other rules and to prove it in general. But just take my word for it, this will work in general, and we can say, for example, that the derivative of x raised to a constant power is going to be nx to the n minus 1. This is a rule. It is actually a very important rule. So important it actually has a name. We call this the power rule. Right? This is the rule for which we can find the derivative of x to a power. right, where the power is a constant. So you can do all sorts of examples with this one. I can talk about something like, what would be the derivative of x to the 7th power?
7x to the 6.
7x to the 6, right? What would be the derivative of x to the 3/2 power?
3/2 over 3/2
3/2
x
x to the,
3/2 subtract 1.
yeah, 3/2 minus 1?
It's 1/2.
1/2. Or I can ask you, what is the derivative of 1 over x to the 4th? And the first thing you would do is you would rewrite that as x to the minus 4, and then you can
It's
use
negative
this rule.
4x to
Minus 4
negative
x to the
5.
minus 5. Or that's minus 4 over x to the 5th. Right? So this rule actually now gives us a shortcut for finding the derivative of anything that looks like that form. If you can write it like x raised to a constant, you know how to find the slope of such a function now via what we call the power rule. So that's a very important rule. You need to know that. Right? And it can greatly simplify your calculation so you don't have to expand a bunch of stuff. In fact, that's kind of what I wanted to use here. I mean, technically we know how to expand the cube now, but it's probably nicer to just think of this as the power rule. You can also think of this as the power rule, by the way. So radical x you could have written as x to the half, and
It'll
you
be
should
1
get
over 2 to
1/2 x to the minus a half, which is 1 over 2 radical x. But let's actually do this by the definition because I need you to know how to do those calculations, and then we'll see that it actually is consistent. So if I want to find the derivative of this guy, that's the limit as h approaches 0, f of x plus h minus f of x all over h. This is the limit as h approaches 0. What does f of x plus h look like?
It will be radical x
Right, square root of x plus h minus
square root.
all over h. How do you find that one?
So you would have to do the conjugate.
Conjugate, rationalize. Right, so you square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. The top becomes the difference of squares, so that just becomes x plus h minus x over h times the square root of x plus h plus x. Here the x's would cancel. Then you'd only have an h on the top, so the h's would cancel. You'd end up with the limit as h approaches 0 of 1 over the square root of x plus h plus square root of x. And at this point, if we plug in h equals 0, you would get 1 over the square root of x plus the square root of x, or 1 over 2 square root of x. And you'll notice here, just to do a check, you can check this with the power rule. So what would the derivative of the square root of x be? Well, that's the derivative of x to the 1/2. Applying the power rule, take the power, move it down in front, 1/2 x to the, take the power and subtract 1. 1/2 minus 1, so it's 1 over 2 minus 2 over 2, you get minus 1 over 2. That minus power says you can bring that down in the denominator, and so x to the 1/2 is that. Right? So it's the same. So power rule is nice because it can save you a lot of calculations, even though these are calculations you should be able to do at this point. So you should remember something like, you can simplify something like this by multiplying and dividing by the conjugate. Let's suppose your f of x is x cubed. This means your f prime, and here I want you to use the power rule.
3x squared.
It's just 3x squared. So this is using the power rule with n equals 3. And we get 3x squared. Right? I mean, if you wanted to do it with something like limit as h approaches 0 of x plus h all cubed minus x cubed all over h. Using the Pascal's triangle, you know that that would be x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. Right? 1, 3, 3, 1. That was on the third line. This would kill that, and be able to factor out an h. This will kill that. Now when I plug in h equals 0, that goes to 0, that goes to 0, and left over the 3x squared. So that's what's actually happening. Right? But you don't want to waste your time doing this all the time when the power rule is just a shortcut to doing that. So that kind of shows you another example of how it will actually break down. What about the cube root case? Right, the first thing is to realize that that's just x to the 1/3. We know that by the laws of exponents. So this would mean that the derivative is going to be, that's x to a constant power, bring the constant down in front, subtract 1 from the power. Whenever you're subtracting 1 from a fraction, just think of it as the denominator over itself. So it's 1 over 3 minus 3 over 3, which is minus 2 over 3. Which, for me, that's good enough. You should also just be aware that that's the same as what? So x squared.
Over 3.
Yes, but what does that mean? What's another way you could write
Oh, 1 over cube root
cube root of
of
x
x
squared?
squared.
You should know the different ways you can write something. Now, on a test, if I ask you this question, that's fine for me. However, on a multiple choice, they might write the answer down in this form. You should recognize that that's the answer. So if you do it and you got this, you should recognize that, oh, it's the same as this. So personally, I don't care if you simplify to this, but you should be aware it could simplify to that in the multiple choice situation. They might write the answer in any way they want. So you should be able to go from your answer to any equivalent answer. So let's look at f of x equals 1 over x. By the way, w. Right. If you're not required to use a definition here, it says you use the definition. But if you're not required, the power rule would have worked here. Right? If you want to talk about the derivative of 1 over x, well, that's just, you rewrite that as how do you rewrite 1 over x?
1 x to the negative 2, I mean negative.
It's x to the negative 1, right, by the laws of exponents. And so now you can actually apply the power rule, bring the negative 1 down, and subtract 1 from the power, get minus 2. So you should get minus 1 over x squared. Let's actually do it by the definition and see if we get the same thing. So f prime of x should be the limit as h approaches 0, f of x plus h minus f of x all over h. So the limit as h approaches 0, 1 over x plus h minus 1 over x all over h. Just look at the function. Everywhere I see an x, put an x plus h. That's what f of x plus h means. How do I simplify that?
So you have to,
Huh?
you have to,
Okay, so the LCD would be x times x plus h. What do I do with that?
and you multiply the whole thing by x. Times
Multiply the whole thing by what? X times x plus h?
I do the top. But I do it by 1 over x plus h times x, and then the other side 1 over x times x plus h, and then I factor.
Okay. We're going to do it by multiplying and dividing by the LCD. That's the fastest way to simplify a complex fraction. This times this will give you x, minus this times this will give you x plus h over hx to the x plus h. X minus x, you get a negative h on top. You can cancel this h, so you get a negative 1 on top. And you're taking the limit as h approaches 0. Plugging in h equals 0, I just get x times x, which is x squared, and I get minus 1 over x squared, which is what we should have done. Fastest way to simplify a complex fraction is to multiply and divide by the LCD. So we looked at the definition, but pretty much everyone we did here is covered by this rule. But it's good that you know how to actually simplify various situations, because they might give you a limit that's similar to one of those. So note all the above examples are covered by the power. The derivative of x to the n is n x to the n minus 1. Right? All of these guys you could rewrite in one of those forms. Even the constant case, you can just think of this as 3x to the 0 and apply the power rule. The 0 is going to come down and kill everything. Okay. So in all these cases, there's an x to the 0 here. Here you have an x to the 1. If you apply the power rule, the 1 comes down, multiplies the c, and 1 minus 1 gives you x to the 0, so the x disappears, and you just look at the c. Right? Power rule applies to all of these examples. Okay. But you do need to know the long way of doing it and the shortcut way of doing it. Now, if a method isn't specified, of course, use the shortcut. There's no reason to do the long way if you don't have to. But you have to pay attention to a problem. It might specifically require you to use the definition, and that means you have to use this formula to compute the derivative. Let's go into another example where it's more like a kind of application, sort of. A very important kind of application, though. So let's follow up with that with very typical problem in a calculus class. So we're going to say use the definition to compute the derivative of x equals 3x minus x squared. That's part A of the problem. Part B says hence find the equation of the tangent to f of x at the point where x equals 1. Let's work through that. Go BTW. Right, whenever it says use the definition, you usually should be able to find it a shorter way, so you can always check your answer and know if you're correct. So if you get this problem wrong, you should know immediately that you got it wrong, and you go back and find your mistake. What would the derivative be here?
It would be
So you look at this part. What do you?
negative 2x plus 3.
Correct. This would be 3. That would become 2x, and you would expect negative 2x plus 3 should be the answer, or 3 minus 2x. Now, I haven't spoken about the fact that to take the derivative of a sum, you can just take the sum of the individual parts. We'll talk about that in a bit, but you can. So you can just take the derivative of this, which is 3. We discovered
I
that
have a
before.
question.
The derivative of that is 2x, and you can come up. Yeah.
But you said use the definition. Shouldn't it be f limit of h?
Yes. Yes. This is just a sidebar.
Oh, okay.
Right? If whenever a problem says this, you should basically do the shortcut to check your work. Right? That's what I'm sure. So we're going to start the problem now. So if it says use the definition, yes, you have to use the fact that the derivative is the limit. Is h equals 0 of f of x plus h minus f of x over h. Okay, what does f of x plus h look like?
It will be 3 parentheses x plus h minus x plus h squared minus 3x minus x squared in parentheses.
Right, parentheses here and here. Right. That's going to be important because if you have to distribute the negative sign and change the signs, and if you don't do that, things that should be canceling won't cancel. So what we're going to do now is pretty much expand the parentheses, right? Multiply out 3, 3x plus 3h. X plus h all squared is x squared plus 2xh plus h squared, but we're taking negatives of everybody. And then distribute this, we get minus x plus x squared. And at this point, we should have a bunch of things canceling. And so you'll notice that the 3x would cancel. You'll also notice that the x squared would cancel. And nothing else cancels, but there is a common factor of h left over. So I can take out that h. 3 minus 2x minus h all over h. This would cancel. And so now you would have, you're taking the limit as h approaches 0, you can now just plug in the 0 because there is no h in the denominator, and you get 3 minus 2x, right? And then you go to the side, do your little shortcut, and like, okay, yeah, that's the same. Okay, so this is right, I know that's the right answer, right? So I ask you a problem like this in the test, and you're doing it the long way, there's no excuse for not getting this right. You know 2 ways, 1 way is extremely short. Right? Doesn't take any harm to just check your answer. Oh, if that's not the same, you made a mistake somewhere. And that's where you start to check, okay, are all my parentheses in? Did I put replace all x's with x plus h, or just put a plus h at the end? Right? You need to look back for the mistakes that you know you're prone to making. Right? Once this part doesn't look like what you know it should look like, you go back and you check. Okay, B. Okay, so how would we find the tangent line?
So you use the tangent line is given the dy over d.
Well, first let's talk about what a tangent line is. Remember, a tangent line is a straight line, right? It's the straight line that we use to approximate the curve, which means it has the formula for like any other straight line, y equals, right? So it's just a straight line. What makes it different? What makes something a tangent line versus any other random line? Sure, computationally though, in the formula, where would the tangent line be different? What's special about it?
Just the slope.
The slope is special. The slope comes from what?
It comes from the secant.
slope doesn't come from the secant line. It's a tangent line.
over
So the m here should be the slope of the tangent line. But what is the slope of the tangent line?
the
This is the derivative evaluated at the point. Right? The tangent line is just a straight line. The only difference is, the thing that makes it special, is that the slope that you're looking for is found via the derivative evaluated at the point. Right? So you don't need 2 points to find that slope. You just need the derivative. That's what makes it a tangent line. So now, if I go to what is the m here, the m is simply going to be the derivative evaluated at x equals 1. Okay, well, what is the derivative? The derivative is this guy, 3 minus 2x. So all I'm going to do is plug in x equals 1 over there. So in this case,
it's 1.
it's 1. So to find the tangent line at this point, it must be a line that has slope positive 1. What I would do now, well, that's the slope. Do we know the point? Well, we know x equals 1, that's for sure. What would the y be?
0.
No, how would you do that?
Yeah,
Yeah, don't bug out.
It's 1.
Just
It's
calm
1.
down. Calm down. How do we figure out the y value?
You have to plug it like
Plug what in?
like the x.
plug in 1.
Plug in 1 where?
Yeah, to the equation, the 3 minus 2, the original function.
The original function. Remember the original function, the whole point of that function is to tell you how to compute the output, the y value. Right? Y is your f of x. Okay? Don't bug out and put anything you want. Just calm down, right? Just understand. A tangent line is just a straight line, like any other line. The only thing that's special, the slope comes from the derivative. Okay, so when I'm looking for the slope of this line, I should be looking at the derivative. All right, I want the derivative at x equals 1, so I plug 1 into that. That's the number 1. Okay, what I need now is the x1 and the y1. All right, so I know the x1, they told me that's 1. How do I figure out the y1? Where do I figure out the y?
Plug into the original.
From the original function. The whole point of the original function is to tell you what the y value is when you know the x value. So I'm going to go here and plug in the 1. And that actually gives me 2. So now I know my x1 and my y1. My x1 is 1 and the y1 is 2. And now I just plug into that formula. The tangent line is going to be y minus 2 equals 1 x minus 1. And in general for me that's fine. But of course on a multiple choice they might write it in y equals mx plus b. All you do is just expand this. That's x
1x
minus
plus
1
1.
and then plus 2. So you can write it as y equals x.
X plus 1.
Okay, now what does that actually mean? If you were to graph this guy, if you look at something like y equals 3x minus x squared, right, that was this would look like that, right? What are these intercepts here? That's obviously 0. Factor this. So what is this guy here? Where is this point?
3.
It's 3. Factor this, set y equals 0, solve for x, that gives you the x-intercepts, right? Now for quadratics, we know that the vertex always happens halfway between this. So it's going to be 3 over 2, right, which is 1.5. Now what they asked you was find the equation of the tangent line at 1. Which means you are now looking at this point, and you want to find the straight line that comes down and touches that point and continues, right? And we now know that that line would be y equals x plus 1. So I know that this would be for 1. So it's a line with slope 1 passing through y-intercept 1. So that's kind of what's happening here. This was the guy who just computed, the blue line. So I can have a function and I can figure out, okay, at that point, what is the slope? And what would be the line that approximates the function at that point? It'll just be the tangent line. What makes the tangent line special is that it's just a straight line, so everything you know about straight line applies. The difference is, you don't use the y2 minus y1 over x2 minus x1. When you're finding a tangent line, you use the derivative, right? Plug in the point you care about into the derivative, that is the slope of your tangent line. You find the coordinates just as how you always find coordinates. Plug in the x, solve for the y in the original function. And then you just plug into that formula. And you can simplify to the mx plus b form if necessary. Any questions? Yes, sir. So, how to compute a derivative the long way, you need to know that. The power rule, you need to know that, so you need to be able to do the shortcuts. And you need to be able to find a tangent line. Right? These are very important skills you're definitely going to be tested on. So, slowly work through, understand where each part is coming from. But we are going to continue to talk about other properties of the derivative that allows us to do other shortcuts. Like the one that we did at the beginning of this. How did I know that I could just take the derivative of each part? So at this point we can talk about the properties of the derivative. As in the algebraic properties. How does a derivative behave under algebraic operations? Let f be a differentiable function. That just means its derivative exists, right? We'll talk about the cases where a derivative would not exist. Its derivative exists. Let C be a constant. Then it turns out that if you are to take the derivative of a constant times a function, the result is going to be the constant times the derivative of the function. In other words, you can factor a constant outside of a derivative. We'll do some examples here. As well as if you have f and g differential functions. If you have a sum of functions, something plus or minus something else, and you want to take the derivative of that, you should be aware that derivatives actually distribute across sums. You can just take the derivative of the first thing and add it to the derivative of the second thing. So, example, like we know that the derivative of x squared is 2x. We just looked at that power rule easily. So now you might ask, what is the derivative of 5x squared, right? So you can need to find that derivative. But this rule tells us that if there's a constant multiplying a function, I can pretty much just leave the constant alone and differentiate the function. So this is like the c, right? So what I'm going to do is I'm going to leave the c alone, and I'm going to multiply by the derivative of the function part, which we now know is 2x. and then I can simplify to get 10x. Right? So whenever I see this, I can think, oh, this is just 5 times the derivative of x squared. That I already know, so that leaves me here in that. Right? Now, of course, in practice, you don't have to write these intermediate steps. You can go from here to here. You should be able to just know, oh, the power can come down and multiply and give you 10, and everything works out nice. Right? If there's a constant in front of it, you just kind of ignore it until you multiply at the end. Leave the constant alone, perform your derivative rule on the function, and then you multiply at the end, and that's the derivative of that new function. So that was an example of one. Another example is, we know that the derivative of x squared is 2x, and we know the derivative of, say, 1 over x is minus 1 over x squared. So someone might ask you, what is the derivative of x squared minus 1 over x? Right? So they can ask you like, okay, let's add two functions together, or take the difference and find the derivative of that. Well, this rule tells us we just need to find the derivative of each individual piece. Now again, you wouldn't necessarily write this out in practice. Maybe the first few times you're doing it, just to get the hang of it, you can just think of this as, oh, I can just differentiate each part. And I know the derivative of this is 2x. And I know the derivative of this is minus 1 over x squared. So this would become equals 2x plus 1 over x squared. So if you have a sum of things, you can just differentiate each part individually. And of course, we can apply both at the same time. So someone might ask you something like, what is the derivative of 4x squared minus 2x cubed plus 3 times the square root of x? Right? So you can just think of that as, this is 4 times the derivative of the x squared minus 2 times the derivative of the x cubed plus 3 times the derivative of radical x. Right? So pretty much the constants stay there, and then you just differentiate the functions beside it. Derivative of x squared is 2x. The 2 multiplied by the 4 will give me 8. Derivative of x cubed is 3x squared. Take the 3 down, it'll multiply the 2, it'll become 6. The derivative of radical x is just 1 over 2 radical x. So this is just 3 times 1 over 2 radical x. And that would be the answer. So these two properties, we can start to find derivatives of much more complicated functions. If anything is combined by pluses or minuses, we can find the derivative of the entire function just by finding the derivative of each part. I'll probably talk about why this is true next time. Right now, let's just stay in computational mode. Keep things simple. So those are some algebraic properties of the derivative. It might seem a bit skimpy, but that's actually on purpose, because what I want you to realize is that morning. Write this down, pay attention to it. Derivatives do not distribute across products or divisions. I.e., for example, if I wanted to take the derivative of one function multiplied by another function, it is not just differentiating each one and sticking them beside each other. It's not going to work. It's not true, right? So derivatives are nice when it comes to constant multipliers. You can always factor them out. It's also nice when it comes to addition. You can kind of just differentiate each part. When it comes to products, it's a little bit more sketchy than that. You can't just differentiate each part and stick them together. It's actually not right. We can know this, for example. Suppose we looked at the derivative of x squared as the derivative of x times x, right? Because after all, that is x squared. If I were to differentiate each part, right? Derivative of x is what?
It's 1.
It's 1. Derivative of x is what?
1.
1. So is the answer 1 times 1? I know that's not the answer. The answer should be 2x, right? So this is just one simple example that tells you you can't just differentiate each part of a multiplication. It's a little bit more complicated than that. So we know it's not the answer. Now next time we'll talk about what the answer would look like. But for now, just know it cannot be done. So you can't just distribute a derivative across a product. It doesn't work. Here's something that is very common to test you on, though. So as far as the algebraic properties are, they're just really those two. Those two are the nice ones. Constants can factor out, it distributes across sums. When it comes to multiplication and division or other types of operations, the derivative doesn't behave as nicely as, say, a limit would. The existence of the derivative is another very important thing. Let f of x be a function then f prime, that derivative limit or just the formula or anything will not exist at any of the following points. Of f. Okay. There are 3 scenarios in which a derivative will not exist. For the most part, you'll be expected to be able to tell these on a graph. So I'll describe the geometrical properties of it. But we'll actually do some examples, calculations. So there are 3 situations in which a derivative will not exist. 1, at points where f has a sharp corner. Fancy word for that is called a cusp. If there's a sharp corner, you cannot actually find a derivative. The derivative limit, it's not going to work. Try to find the limit, use the limit definition, you'll get the limit does not exist. Right? So if you have like that, or that, or that, right? So at these points here, you don't have a derivative. If your function goes through a sharp corner, it will not have a derivative at the sharp corner. That's one situation. We'll actually do a computation that talks about this. But one way you can kind of see that this would have to be the case is that what would a tangent line look like going through a sharp corner? Is that a tangent line? Well, it only touches it at one point. So does that. So does that. So does that. And in general, none of them are really better than the other one, right? Because if you zoom in, this point of the function is not going to look like anything. No matter how much you zoom in on a sharp corner, it will never flatten out. Remember, we found a derivative by thinking of a curve as, oh, if we zoom in, it'll flatten out, and then we can use a line. It'll look like a straight line if you flatten out enough. The thing is, a sharp corner will never look like a straight line, no matter how much you zoom in. It's a sharp corner. It's never going to look flat. Right? So anytime you zoom in on a sharp corner, it's never going to look like a straight line. It'll always look like a sharp corner. And so there's no correct way to draw a tangent line through it. So what is the slope of the tangent line? I don't know. I don't even know what line I should be drawing right now. You won't be able to get a tangent line at a sharp corner. So whenever on a graph someone asks you, pick out the points on this graph where the derivative does not exist. Sharp corners are going to be one of those locations. You'll know that, oh, here it's not going to work because there's a sharp corner. The second kind of point where a derivative does not exist. At points where f is discontinuous. Again, that one should be kind of obvious. If there's a gap, no matter how much you zoom in on a gap, it's not going to look like a straight line. It's a gap. There's nothing there, right? So if your function has like a hole, right? You can't draw a tangent line there. There's no coordinate to plug into the line, right? There's no coordinate there. There's a hole. No matter how much you zoom in, there's always going to be a space there. There's nothing, right? Right? So over here we can zoom in, it'll look like a line. Over here we can zoom in, it'll look like a line. But at that point, it's a gap. If I zoom in, there's just going to be emptiness. There'll always be emptiness. It's a hole. Right? Similarly, if your function does something like this, right? Again, zoom in on that gap. It's a gap. It's never going to look like a straight line. Right? So if we have, this is like x, y, and then that's a. This here is the x, y plane, and then that's a. You would be able to tell here that f prime of a does not exist. Okay. So wherever there are sharp corners, you can't find a derivative. Wherever a function is discontinuous, there's a jump, or there's a gap, or there's a break, or there's a hole, you can't find a derivative either. It will never look like a straight line no matter how you zoom in. There's one other situation which is not a very common one to test you on, but I'll mention it anyway. It's not common because it's hard to tell on a graph when a graph actually does it. But these, you should be able to look at a picture and it should be easy for you to identify a sharp corner and a hole. The third one is at points where the tangent line is vertical. Right? Certain functions have this property that when you zoom in, if you want to draw a line that behaves like the function, a vertical line is the best line to draw. So you would have a function that's doing like, you know, it's decreasing rather slowly and it gets very, very steep, and then all of a sudden it switches its behavior suddenly, right? Now at this point it's not a sharp corner and it exists there, but it turns out it gets so steep after a while that if you zoom in, the best line to fit on that curve would be a vertical one. Right? Like zoom in the best line, the one that is going to describe the behavior the best is going to be a vertical line. But we know that vertical lines have no slope. also remember that slope is just another phrase for the derivative. So something that has no slope consequently has no derivative. So there are times when the best line to describe the function is a vertical one. And at such points, you won't be able to find a derivative. Right? So you'll have functions that have that kind of behavior. Right? They're just very, very steep in a certain region to the point where they're almost vertical. Of course, they can't actually be vertical because that would break the vertical line test and it wouldn't be a function. But you have functions that they go pretty much vertical for a single point and then they change that behavior. And at points like that, you can tell. So this is kind of hard to actually see on a picture when that's happening though. But these are easy. So you should expect like pictures like this. And the common example for this one is looking at the absolute value function at the origin. So let's actually do a computational example of that one. Example of type 1. If you consider phi equals the absolute value function at x equals 0. So we all know what that function looks like. It's just a p. So there's a sharp corner here. You might not be convinced that there's no tangent line there. So what we can do is let's actually find the slope of the tangent line here. But that is just f prime of 0. And f prime of 0, let's look at the definition so you can actually see it a little bit clearer. That's just f of 0 plus h minus f of 0 over h. What is f of 0 plus h? Well, that means I go to the original function. Everywhere I see an x, I plug in as 0 plus h. What is f of 0? That means I go to the original function. Everywhere I see an x, I plug in as 0. Limit. So that's just basically that. This comes down to that. Now, how would you find that limit?
Start approaching 0.
Start approaching 0.
Or input 0 for the h's and then 0.
You put,
Well, you can't. There's a 0 in the denominator.
you put numbers that are like close to 0.
Okay, and how? Well, there's an absolute value. Well, how does the absolute value behave?
Any numbers that positive, it will be positive.
Absolute value of x. Define. What's the definition of this function?
Natural. 1 over. It's just x.
No. How do you define the absolute value function? Someone should know. Covered it several times. What is the equation on the right side?
It's the same distance to the left.
Sure. What's our formula? A way to write that down.
X is greater than 0.
It's one thing when x is greater than 0 from when x is less than 0. So absolute value is a piecewise function. It tells you something when you're greater than 0, something when you're less than 0. What are those things? When we're greater than 0, what is the equation here?
0 positive.
If I pick a number 2, what is the corresponding output? This would be the absolute value of 2. What is that? 2. Every number will be itself, y equals x. What if the number is negative? Pick like a negative 2.
It will be 2.
It will be 2. How does 2 relate to negative 2?
Because it's y.
Well, it's the negative of negative 2. That's the absolute value function. You need to know that. Okay. So the limit here is approaching 0. It involves an absolute value where the inside is going to 0, which means it's going to split the limit. You're going to have to worry about a left-hand limit and a right-hand limit. This is h. Now when you're coming from the left, you're a little less than 0, you're negative. The absolute value function is going to return minus h. If you're coming from the right, you're a little positive. The absolute value is going to turn h itself. You realize, what's the limit in the top case?
It's negative.
How do you find the limit of that as h goes to 0?
It's negative 1.
Okay. What are the strategies? Space with a random limit. What are the steps you go through?
The plugins.
You try to plug in. Can we plug in? No, there's a 0 in the denominator. What's the second step?
Simplify.
Try to simplify. Can you simplify that?
Yes.
Cancel the h's. Minus 1 is the answer. Remember the strategy. You shouldn't be confused or stuck. There's always a sequence of steps you should go through. You need to know the steps. Know the definitions, know the steps. Here's a random limit. First thing I'm going to try to do is plug in. Can't plug in because the denominator is 0. What's the second step? Simplify to plug in.
So
Yes, I can. Cancel. 1. Okay. So now we have a problem. The left side is giving us negative 1. The right side is giving us positive 1.
it's discontinuous.
Does not exist. Right? Because this function behaves like a 1 over here, technically can't add 0, and a negative 1 over here. There's a gap. This function, that's its picture. It's a 1 on the right side, it's a negative 1 on the left side. That's a jump. So the limit does not exist. Okay? So when we try to compute f prime for this particular function at that point, we end up computing a limit that does not exist. And something like this is going to happen at any sharp corner. Right? Your dirt is going to end up splitting into parts where on one side versus the other side, it's giving you different answers. Right? So on coming from this side, the tangent line might want to measure that side of the function, but then if you come from this side, the tangent line might want to measure that side of the function. These two slopes contradict each other. Right? If you're traveling along from the left side, the tangent line will probably want to continue horizontally. If you're traveling down from here, the tangent line is probably want to be doing that. Again, they contradict each other. Right, so sharp corners actually don't work. And this is it's a very common computational example. Pretty much any textbook that talks about this kind of situation, that's the example they're going to come up with. And they expect you to know how to actually compute that limit. Let's quickly do some derivatives by shortcuts, and then I'll show you how to do it on your calculator, and then we'll stop. It should only take a few seconds. It's really just applying the power rule and the properties, and it's find the derivative. So note that it didn't say use the definition, it just says find the derivative. So the method is up to you, but I'd probably choose the easy method.
Excuse me.
Okay, let's look at E. Y equals 2 over x. How are you going to find the derivative? How do you find the derivative of 2 over x?
So it will be 2, and then you put x on top, so it's going to be x to the negative 1. And then you bring down the 1 to the coefficient, so you multiply it, and then you subtract 1 from the,
So we do what?
it's going to be negative 2.
Rewrite it. Why do you rewrite it? So it looks like the power rule. There's a rule that tells us how to deal with a situation where we have x raised to a power. So I rewrite it, so I have x raised to a power, then I apply the power rule. Bring the power down, subtract 1 from the power. That's your answer. What about x squared over 2? What would you do there?
I'll multiply it by the reciprocal, so I could get the 2 up to the numerator, and then subtract.
So we're going to talk about this more next time, but the trick here, whenever your denominator is a constant, you kind of just leave it alone and differentiate the numerator. Derivative of x squared is 2x. That cancels, that becomes x. Now y, it's kind of like what you said, but I wouldn't go all the way as thinking about reciprocals and stuff. Just realize that x squared over 2 is the same as 1/2 x squared. You can like slide it off, right? So there's really a 1/2 in front. And so we have a rule that says if there's a constant times a function, leave the constant alone and differentiate the function. But that of course can be written as this. You can slide the 2 back under, right? So whenever you have a constant denominator, you can slide it in and out from the denominator at will. That's just how fractions work. And so what can happen is, if you have a function divided by a constant, leave the constant alone, differentiate the top. If you have a constant on top, what you would do is move whatever function is down on the bottom up using the laws of exponents, and then you can do the derivative rule there. So this is telling you, they're not meant to be complicated examples, but they're kind of showing you some important algebraic manipulations. Constant on top, bring the denominator up and use a derivative rule. Constant on the bottom, leave it alone, differentiate the top. What about this one? So that one's kind of straightforward. Leave the constant alone, differentiate the function part. 5x to the 4th, so you get 15x to the 4th. What about this one? Derivative of this? 8x cubed. 4 comes down, multiplies the 2, and you subtract 1 from the 4. What about this one? Minus 6x. 2 comes down, multiplies the 3. 2 minus 1 is 1, so I just get x to the 1. What about this one? Minus 1 over x squared. Or you can just realize that this is x to the minus 1. So its derivative is minus x to the minus 2, which is going to be that. That's that. Differentiating things like this shouldn't take you any time. Well, this one's a little bit complicated. How do you do this? Say the trick here. Remember, this is something we'll deal with next week. We're going to do not distribute across divisions, right? So you can't differentiate the top and differentiate the bottom. That's very wrong. However, we only have a single thing in the bottom, so simplifying becomes an option. I can actually simplify this by just dividing this part into each piece. So I'm not differentiating here, I'm just simplifying. Here, this will cancel into that with a square, this cancels into that. So this is 1/2 x squared. This will be, the x's cancel, this will be 3 over 4. And here, this will cancel into that, half power. So this is 1 over 4x to the half. Can I rewrite this somehow? In the denominator? So plus 1. How would you rewrite that? This expression. Maybe there's a better way?
Over x squared.
4 over x squared. A better way, especially considering the rules that we want to apply. I really only gave you one general rule for derivatives so far, right? It's the derivative of x to the n is nx to the n minus 1. Given that I know what rule applies to something that looks like this, how would I want to rewrite that? You know, there's no fraction. How would you rewrite that over x squared?
1/4 x to the 1/2, and then you do, and then
What do you mean 1/4 x to the 1/2?
I was doing something else, never mind.
So very simple laws of exponents, guys. How would you rewrite 1 over 4x to the half?
Or you do the bottom, 4x. So it'd be like square root of 4x.
So I have a rule. 1 over x to something is what?
X is singularity.
How would you rewrite that?
1
So
over
1 over 4x.
4x to the negative 1. 1/2.
4x, x squared?
4x to the negative 1/2? Not correct. What's the problem?
Because it's a 1 on top.
What's the issue here?
The
The 4 is the issue. So how would you correct it?
4 is
So it'll be
x to the
x
negative
to
1/2 over
negative.
The 4 is still in the bottom, right? The half power is applying to the x only. I can bring that up with the law of exponents, but the 4 does not have a power. He stays down. Okay? So starting here, I split it into 3 parts, simplify. The rules tell me what I'm allowed to do. I do not have a rule that has a x in a denominator. I only have a rule that tells me how to deal with x to a power. So if I'm going to apply a rule, I have to write everything so that it looks like x to a power. X to a power. So then I'm going to think, what allows me to write 1 over x to the half as x to a power? That does. Bring it up, make the power negative.
But I thought you said that there's supposed to be no fraction.
No fractions were. I'm saying this rule doesn't have a fraction. This isn't a fraction. This is x to a constant. If you look at 1 over x to the half, this part here, the 1 over part, it's not in the rule. Right? There's no 1 over here. Right? I just have x to a number. So if I see 1 over x to something, it doesn't look like x to a number. I need to rewrite it. By using the laws of exponents, now it looks like x to a number. X to a number. X to a number. This doesn't look like that. This does. The rules are going to be very important. They're going to tell you what you're allowed to do in which situation. And in order to apply a rule, you need to make sure whatever you're applying it to looks exactly like what's on the left side of that rule. And then you're going to apply the rule by applying the right side. So because x is in the denominator, this rule does not apply. If I bring it up and write it as x to a power, okay, now the rule applies. It did not apply before. It's very important that you know that. If you try to apply the rule in the denominator, you're going to be wrong. So you can't bring this half down and then subtract that half from there. That would be the wrong answer. Okay? You have to rewrite everything so that it looks like the rule you want to apply. So that x being in the denominator was a problem. Bringing it up, which I know how to do by the laws of exponents. Now I have x to a power and x to a power. This guy is a constant, which we have our own rule for. So now we can finally take a derivative. This one will become 1.
It would be 1 half times 2.
Right, so just x, because the 2 comes down, kills the half, you have x to 1. What's the derivative of the constant?
It's the same.
0. You know that's a general rule. Derivative of any constant is 0. Over here,
It's negative 1 half times 1
so it's minus 1/8.
Raised to negative.
Right, because it's 1/4. I bring down a minus 1/2. That gives me a minus 1/8. X to the
Negative. So negative 1
minus
half.
3 over 2. That would be the algebra is important. Just because we're doing derivatives now doesn't mean that algebra ceases to be. Laws of exponents apply, factoring applies, everything else applies. You have to remember everything that we've been doing from the beginning. Turns out your calculator can actually do derivatives pretty easily. So if you just pull those out, I'll show you. Maybe we'll do this one. Although it'll probably combine the fractions, but we'll see. We can do some of these. So if you're in the calculator section, you need to find the derivative for some reason. Here's how you're going to do it. Step 1, as always, is to turn the calculator on. So let's say I wanted to find the derivative of the 3x to the 5th, right? That one's pretty easy. Okay. So the rule is the function is in here, in F3, calculations. So you're going to press the F3 button, and there on the very top is D for differentiate. Right? So you're going to click that. Okay, so you have that. And what you're going to do is, because the derivative can talk about any variable, so it's going to be D parentheses, you're going to type the function, comma, and x. Right? So x is going to be the independent variable here. So you can type out the function, comma, x, and that says you're taking the derivative with respect to x. So let's look at 3x raised to the 5th, comma, x. So you go F3, choose derivative. The D is going to pop up. You're going to type the function that you want to find the derivative of. Then you're going to put comma x. Again, because this function can talk about several variables, you really want to tell it what your variable is. So you put comma x. Now if you press that, we know what we expect the answer to be at this point. 15x to the 4th.
Where's the comma?
Huh? Yeah, you probably can't see, but there's a comma right here. It's D, open parentheses, I type the function 3x to the 5th, I put a comma, and then x, and then close the parentheses.
I'm blind, sorry.
Let's do it again for, say, the x squared over 2. Let's say I go to differentiate x squared divided by 2, comma, x. Right, so remember the comma is right here. Okay, this is 8. Right, so that's basically it. You can look at the other examples that we did and just try to see if you get the answers that we got, which should be the right answers. So yeah, F3, go to differentiate, it's going to be the first option. It'll open D parentheses, type the function, comma, x, and that tells you. And then once you press enter, close the parentheses and press enter, that gives you the derivative. So we'll stop there. I will post the review for the test next week. Later today, you guys can start working on that. We'll cover everything up to this point, so it's basic derivatives.
Wait, so the test is next week?
Yes.
You're gonna